Hi, welcome. All right, so in this set of notes, which is going to be a second set of notes on our solutions unit, we're going to focus primarily on reference table F. So you should have your reference tables out to reference table F, where we are going to talk about the solubility of different compounds, specifically in aqueous solutions. And again, aqueous, right, means AQ, and that has to do with being dissolved in water, H2O. Oh, terrible. I hate this stylus. One of these days, when we're out of our uh, isolation, I will go and buy a new stylus. I'm going to switch to tablet mode. All right, so while you get your notes out, right, so we're on our notes book 2, and we're going to start. Okay, so why do some things dissolve and some things do not dissolve? So basically, the most important factor is going to be what we call the nature of the nature of the solute, right? What's being dissolved, and the solvent, which is what's doing the dissolving. What are the two things or more that you're trying to mix together? So basically, it all comes down to what we did in our bonding unit, which is like dissolves like, right? So that means that only things that are like each other can basically dissolve in each other, right? This is why oil and water don't mix. So if I have something that's nonpolar and nonpolar, right? Nonpolar, nonpolar, we're going to say that is soluble. Okay, so soluble. That means it will dissolve. And now if I have a nonpolar and polar, they're different. So then we're going to call that insoluble. So then that's insoluble. Okay, so what about the same thing going down here? Polar, nonpolar, right? Those are different. So we're just going to call that insoluble. I'm going to just abbreviate. And then polar, polar, soluble. And then if I have an ionic solute, what the heck is ionic again? Remember, ionic is a metal plus a nonmetal, right? Or anytime you have a polyatomic ion from table E, you also have an ionic bond. So in a nonpolar solvent, they're going to be insoluble, right? Because there's no charge. But in a polar solvent, there will be soluble because of the charges. Okay, so water and styrofoam, are they soluble? No, I'm not going to demonstrate it, but you've probably seen it before, right? This is why your coffee doesn't dissolve your coffee cup, right? If you have a styrofoam cup. But if you took acetone and nail polish remover, would that dissolve? Yes. So does that mean styrofoam is polar or nonpolar? That means styrofoam is nonpolar because water is polar, right? Asymmetrical and symmetrical, right? Asymmetrical, symmetrical. SNAP, remember? Symmetrical, nonpolar, asymmetrical, polar. So if acetone and styrofoam dissolve, right, that means that they are both going to be the same polarity. Okay, so for solids, the main factor is temperature. As temperature increases, the solubility, oops, oh, now I got to fix that. Let me just go all the way up here. The solubility increases. Okay, so there's table G that's going to tell you, right, the slope. But for most gases, as the solubility increases, so as the temperature increases, the solubility, which I'm going to just do SUL, decreases, right? Carbonation is lost. So if anytime you've ever tried to dissolve sugar, right, in tea, like iced tea or hot tea, it's always going to dissolve in the hot tea faster than the cold tea, right? Because of the temperature, which has to do with the kinetic energy. So let's talk about pressure. So for solid or liquid, there's no effect. So there's no effect. And why is there no effect? Because you cannot compress the particles in the solid or the liquid. But for gases, right? So with our gases, right? Our gases have particles that are really far apart from each other. So as we add pressure, we can push those molecules closer together. And then we can take the gas, which can become a liquid. And if we add pressure and cool it down, right, and make it colder, we can even get that gas all the way down to a solid, right? So basically like dry ice, right? Because carbon dioxide is a gas. We can then make carbon dioxide a liquid and then carbon dioxide as a gas by adding pressure. So for gases dissolved in liquid, as pressure increases, what happens to the volume? The volume decreases, right? So we did that in our gas laws unit. So then the solubility will increase. So what does this have to do with like our gas laws unit? So remember, an ideal for a gas is going to be that high temperature and low pressure. So then that's going to have a gas able to spread out. If you want a gas to be dissolved in something, that's the opposite of spreading out, right? It's putting it into something. So then for a gas to be soluble, we have to do the opposite of ideal. And what is the opposite of ideal? Well, if ideal is that high temperature, low pressure, right? Summertime, temperature's high, pressure's off. All right, so then the opposite of ideal would be low temperature and high pressure, right? That's how they do the bottling of soda. Okay, so let's go on. We are going to go to the next page. So we're going to talk about solubility in table F. All right, so table F in your reference tables is probably the worst designed table you've ever seen. So basically what it's going to do is it's going to tell us if something is soluble or insoluble. That's an O. Insoluble. I'm going to make this bigger. I've got better handwriting if it's bigger. Okay. And so it also is going to allow us to predict a precipitate. Okay, so that's like what? You're like precipitate. Precipitation. Are we talking about like rain and snow? I'm not talking about rain and snow, but what do rain and snow do? They kind of fall from the sky. So basically, a precipitate is an insoluble product in a chemical reaction. And it basically falls. Ooh, don't know why that's zooming like that. It basically falls out of solution. And so it basically just gets like all yucky. Okay, so let's take a peek at this reference table. All right, and we'll talk about how it is a poorly designed table. Okay, remember ions, right? Ions are positive or negative. For the most part, there's only two positives. For the most part, we're looking at the negative ion. So basically, you're going to look at or examine your negative ions mostly. Okay? And remember, ions are positive and negative charges, right? Cations are positive, anions are negative. So then these are the ones that are soluble. What does soluble mean? That means these will dissolve. And so then these ones are, so it's basically, this is two separate tables. And we got to look at it as two separate tables. And so if this side of the table is the soluble side, this side is the ions that are insoluble. So these will not dissolve. In aqueous, right, that means water, right? Okay, so let's take a look at the left-hand side. Let's look at the will dissolve side. All right, these will dissolve. So anything in group number 1 on the periodic table will dissolve. No exceptions. None, right? No exceptions. Everything in group 1, no matter what, dissolves. Anytime you see an NH4, it will dissolve. No exceptions. Anytime you see an NO3, right? So now we're looking at the negatives, right? So this is going to be the second one in a formula because we always do positive first, negative second. Always soluble, no exceptions. Always soluble, no exceptions. Always soluble, no exceptions. Always, always. So always, right? If there's no exceptions, it's always soluble. So I'm just going to do like this, and I'm going to do always soluble in water. But now let's cut this off right here. So now your halides, right, which is your group number 17 on the periodic table, are soluble. Exceptions. That means they're soluble unless they get together with silver, lead, or mercury. So for example, if I have AgCl, that would not be soluble because chlorides are soluble, except if it happens to get together with silver, then no, right? Because the exception makes the rule opposite to the rule. All right, so sulfates are soluble, except if I have one of these elements with the sulfate, right? So if I happen to have a barium sulfate, it's not soluble. But if I have sodium sulfate, well, sodium is not one of the exceptions, so yep, soluble. Okay? All right, let's go on to the insoluble. So these two sides of the table really work together because the exceptions for the insoluble kind of go together with the always soluble ones on the other side. So let's take a peek at the carbonates here. So let's change color. So if it won't dissolve, let's go with red, right? Insoluble. All right, so carbonates are insoluble, except if it's with group 1 or an NH4, right? That goes with over here, right? With group 1 and NH4. So how do I know? So if I have sodium, that's an Na. Oh, terrible with this pen. If I have sodium carbonate, will it be soluble? Well, carbonates are insoluble, except if it's with something in group 1 or an NH4. Is sodium in group number 1? Yes. So then this would be soluble. But if it's with anything else, like if it's with iron, then no, because iron's not in group 1 and iron is not in NH4. So chromates are insoluble unless, again, with group 1 with an NH4 or if it happens to be with calcium or magnesium. Okay, so insoluble, the exception makes it soluble. So now these are soluble. So if there's an exception, the exception is insoluble. Okay, it makes a little more sense. Let's do some practice. All right, so how to use this table. Okay, so you basically want to look at the negative ion, right, which is usually the one that's listed second in the formula. All right, and then you want to check the exceptions. Oops. You know I can't spell. So exceptions. All right, check the exceptions. Okay, and that's basically it, right? Look at the negative ion, check the exceptions. All right, I'm just whittling this down to the bare bones. So now let's take a look at, let me just zoom out a bit so you can see the formulas and the table. And I'm going to do a little bit of erasing so that we can make sure we can read the table. All right, so while I'm, frantically erasing, why don't you look at this first one, which is potassium, which is K, and NO3, which is nitrate. Okay, so K with an NO3. So remember, I am looking at the negative ion. So where is the negative ion? Okay, so where is that negative ion? What color are we going to choose? Oh, my, so many choices. Let's see which one I have not used. Oh, let's try this pink. Okay, so I have potassium and I have nitrate. So I have an NO3, right? Because I'm looking for that negative, right? So this NO3. So where is NO3 in my table? I scan the table till I find NO3. Okay, so here is NO3, nitrates. Are nitrates soluble? Yes, they are soluble. Check my exception, no exceptions. So no matter what it's with, it's soluble. All right, so now let's check on our next one, which is calcium carbonate. So now let's find our CO3 because we're looking for our negative ion. So there's our CO3, right? We're matching. So carbonates are insoluble. Aha. Okay, so now check my exception. Is it in group number 1? Is it with group number 1 or is it with an NH4? Well, it's with calcium. But if I don't remember what group on the periodic table calcium is in, let's take a quick peek. Okay, so I don't know what it is. Where's calcium? Right? Go back and look. Make sure you know. Oh my goodness, so many reference tables. Oh, where's calcium? All right, there's calcium right there. Calcium's not in group number 1, it's in group number 2. So since calcium is in group number 2, that makes it the exception, right? So if it's insoluble, the exception, soluble. Okay, so far okay? If not, rewind, listen again. All right, you try this one. Pause if you'd like to. Try magnesium sulfate. Okay. Hopefully you paused and you tried it. Now you're checking to see if you're right, or you just waited for me to go on to the problem. Okay, so I'm checking SO4. Find SO4 on your table, scan it, look, make sure you're reading very carefully. Oh, SO4, where are you? Where are you? Okay, there it is. SO4, sulfates are soluble. Okay, now check my exception. Is it with one of those guys? Is Mg one of those? Mg is not one of those, so it is soluble. Now let's look at NH4OH. So find my OH, hydroxides. Okay, found my negative ion. Hydroxides are insoluble. Okay, so now check if what it's with makes it an exception. Well, it's with NH4, which is an exception. So if this is insoluble, the exception is soluble. Right, that's table E. Okay, it's kind of like the worst table there is. But you know what? I'm hoping that you go through and you go back and you redo a couple of those. Okay, so now solubility is basically a measure of how soluble something is in a specific solvent. So if we say something is soluble, it will dissolve. Right? So then it would be soluble on table F would be have the most amount of ions, right? So then that's what we would say for the most amount of ions. We would call this the most soluble. Or we would have the most ions. Oops, not MOR. Most soluble. And if something is soluble on table F, it will have the greatest amount of ions. Great. Oh my gosh, why can't I write today? Goodness, guys. It'll have the greatest amount of ions. Now, if something is insoluble, right, it would be insoluble on table F, and it would have the least amount of ions. So insoluble, but basically it will not dissolve. Okay, so then what does that mean? Well, there's soluble and insoluble. Well, there's different amounts that can be dissolved, right? If I decide like I like tea, but maybe I like a lot of sugar in my tea, right? So, or maybe I just like a tiny bit of sugar in my tea. Well, how much sugar is in my tea would be a measure. I could measure that, and we would call that concentration. Concentration just basically means a ratio between the solute and the solvent. And we can express that in a bunch of different ways, right? We can just express it in qualitative words like soluble and insoluble. And we can express it in qualitative words called dilute and concentrated. So basically, if something is dilute, it's going to be very weak, not a lot dissolved. So not much solute, not much solute. Oh, come on. There we go. Oh, don't you love when technology doesn't want to work? Not much solute, right? That's why I've got this tiny little solute and a large amount of solvent, right? Tiny little sprinkling of sugar in my tea. Now I can have concentrated, which is going to be a strong solution. That means there's going to be a lot dissolved of the solvent, a solute. Lot dissolved. Okay, lot dissolved, right? I have a lot of sugar, a lot of solute in a tiny little amount of solvent, right? This is where you could just make something like rock candy, if you've ever made that, which is amazing and it's delicious. All right, so most and least concentrated, according to table F, right? Because what does that all have to do with table F, right? If something is going to be the most concentrated, right? Concentration, I'm going to make this a little bigger so that I have better handwriting, sort of, right? So concentration is directly related to the amount of solute dissolved. Whoops, don't know why that did that. Dissolved. So the most concentrated would be anything that is soluble, right? So this is going to go with table F, okay? If whatever is the most concentrated will be the only one, and it's going to be multiple choice, right? It's always going to be 3 the same, 1 different, multiple choice type question, right? You'll have 3 soluble, 1 not soluble. So what's the answer? The one that's different. Or you're going to have 3 not soluble and 1 soluble, right? You're going to choose the one that's different. The least concentrated would be insoluble, right? Especially in terms of ions, right? All right, so chemical reactions in table F, we are going to skip, okay? So basically, we're going to skip this. Why are we going to skip it? Because I don't want to do it, and it is not necessarily on the Regents exam, so we're going to just focus on the basics. All right, so now we're going to go to calculating. So now these are all going to be what we call quantitative concentration. So this is where we're attaching numbers, right? We're going to do a lot of math here. So we're going to go to, and I'm going to do the bottom first, right? Percent by mass and percent by volume. So percent by anything on table T, right? Your formula for percentage, right? Your percentage is equal to the mass of your part divided by the mass of the whole. And then please don't forget to multiply by 100 times 100. So what is the percentage of mass if 2.5 grams is added to 50 grams of water? Okay, well, my percentage will be equal to the part, right? That's what I'm trying to dissolve, 2.5 grams divided by the mass of the whole. Well, I have 2.5 grams and I have 50 grams of water. Add those two things together, give it a stir. Do I have 50 grams of water? No. Why do I not have 50 grams of water? If it says water, that means that you have to add your solute and your solvent, right? The law of conservation of matter states matter cannot be created or destroyed. If I add sodium hydroxide or anything to water, the mass of that substance doesn't disappear when it dissolves in the water. It's now added to the mass of the water. So now really what I do have now is 52.50 grams, right? Because I have to add these two things together and then multiply times 100, right? If you see correct numerical setup and you don't have the times 100, you don't get credit. Okay, so then that is going to be about 5%. If you do it on the calculator, it comes out to be 4.762, but we're just going to round that to 5%. or 4.8. Okay, so 4.8%. Okay, so now percent by volume. It's still a percentage, but now we're doing it by volume instead of by mass, right? So this is kind of like, I don't know, 70% rubbing alcohol. That means 70 out of every 100 parts of that solution are what? Are rubbing alcohol, and the other 30% is water. So then I'm going to take my volume of the part divided by the volume of the whole, and I'm going to multiply by 100. So now what is the percent by volume of alcohol if 50 milliliters is diluted with water to form a total volume of 300? Okay, so the volume of the part is, so my volume of my part is equal to 50.0 divided by the whole. Do I have to add these things together? In this case, no, because it says total volume. So the total volume is 300. If it said to water, then yes, you would have to add them. Don't forget to multiply times 100. And this is going to be 16.7%. Right, so now let's go up to the top, right? There's percentage, right? Just by being the math students that you already are, you should be able to do percentages. So now let's look at parts per million. Okay, so this is how things are often, shown in air quality and water quality reports, either parts per million, ppm, or parts per billion, ppb. So your formula is on the reference tables. ppm is equal to the mass of your solute divided by the mass of the solution. And this is not a percentage, so I don't multiply it by 100. It's a part per million, where 100 is a part by 100. So then I have to multiply by a million, which is 1, and it has 6 zeros, right? Copy it down on your reference tables. Okay? So now let's take a look at our question. We have 0.0043 grams of oxygen can be dissolved in 100 milliliters of water at 20 degrees. Express this in parts per million. So my parts per million is equal to the mass of the solute. Okay, so that's what's being dissolved. 0.0043 grams of that oxygen divided by the mass of the solution. Well, I'm adding this amount of solute, right, the oxygen, to water. It doesn't say total solution. So that means if I see water, that means I have to add these two things together, right? That means I have to add. So I have 100.0043. I know it looks like you're not adding a lot and you think it doesn't matter, but it really does. And then times a million. 1, 2, 3, and then 4, 5, 6. So this comes out to be 43 parts per million. So it means out of every 1,000,000 parts of water, 43 of those are oxygen. Okay, so now we have molarity, right? Molar, which has to do with the mole. Oh my goodness, the mole again. Yep, chemistry repeats itself, right? Okay, so now on our reference tables, capital M is molarity. Molarity equals the moles, right, of the solute divided by liters of solution. Notice it doesn't say anything else. It's not moles of solution. It is liters. It has to be liters, right? So if you have to convert between milliliters and liters, you may have to. So now what is the molarity? That's what I'm looking for. Of a solution, I have 4 moles, right? That's my moles of solute. So 4.0 moles divided by, and here's my solution. There's my liters. There's my 0.50. So 4 divided by 0.5, and that's going to be equal to 8.0, capital letter M, 8 molar. That means that there are 8 moles in every of sodium hydroxide and each liter of solution. All right, so this is going to wrap up this section of the notes. Oops. And what I'd like you to do is you'd like you to make sure you do some practice problems, right, from this unit. So you do have some practice problems in the unit towards the back, right, where you have a molarity worksheet in the back. If you're given grams and you need molarity and you need the molarity formula, you need to convert to moles first. Okay, using your mole formula on table T. Okay, but this would be considered advanced, which you won't be asked on the Regents, and I will not ask you on tests or quizzes. Okay, remember, if you have questions, please message Mrs. Mitiga or myself on Google Classroom or send an email. Make sure you log into Zoom during a Zoom meeting, right, so that you can ask questions, right? Make sure you're an advocate for yourself, and you can always, use other resources I'd be happy to help you find. All right, until our next set of notes. All right, see you later.